Okay.
Okay, welcome to Let's Discuss a Paper right after reading it. Um, Today we have two people, me and Yota.
Yeah. I'm Yota Kashima. I'm a research engineer in Japan.
Yes, and I am Qian Chen, and I'm currently a PhD student at Monash University. So today we chose a paper 2 hours ago, and then we read it, and then now we come back to discuss it. So the paper we read today is by Xu et al., published this year on PNAS, titled Search of Neurophysiological Coupling and Connectivity of Gamma Oscillation in Dying Human Brain. So first I'll give a summary on this paper, and then we'll discuss any comments and questions we have. So I'll give the summary. This paper, as the title suggests, it focuses on what happens to the brains when people are dying. And our common understanding of the dying human brain is when the heart stops beating, the brain also becomes gradually inactive. And that kind of makes sense if you only look at the behavioral responses of the patient, in which they just become irresponsive and suggesting maybe they have lost consciousness, and that corresponds to brain becoming gradually inactive and gradually unable to support consciousness. However, a very perplexing phenomenon is that some survivors of cardiac arrest, so survivors of people who was found to have their heart stop beating, but then they were, they survived it. They came back to life, and they reported near-death experiences. And according to them, when they are dying, they have a very strong conscious experience, and they felt that kind of experience so strongly that they feel the experience is even realer than their everyday conscious experience when everything of their body is functioning just fine. And so there's this obvious contradiction between a proposed inactive brain and the very strong near-death experience. And recently, to solve, as the first step to solve this contradiction, the authors, so the same team, found that animals suffering cardiac arrest show heightened gamma band oscillations across the whole brain, and also global increase of functional connectivity in this band. And this finding is very interesting because gamma band activity, which is just high frequency brain signals, has been suggested to be a candidate neural correlates of consciousness. And if we find high frequency oscillations in dying animals, then it could be just the key to answer why ND exists. And aside from finding the possible signature of ND in dying animals, research on visual consciousness also suggests the possible location in the human brain for this signature to happen. More specifically, near-death experience tends to be highly visual. So, for example, a lot of people report they see their whole life's memory flashing in front of them. And this predicts that the signature will likely be in the posterior hot zone, or another name of it is temporal parietal occipital junction, TPO junction. This area is critical for visual spatial processing, and the action in this area predict not only contents of perception of external stimuli, but also the perceptual content of these internally generated perception, for example, dreaming. So the kind of prediction that the authors make on the dying brain of humans is relatively clear, which is gamma band oscillations happening in TPO. And therefore, the aim of this study is basically to verify this prediction somehow. Investigate the neuroactivity of the brains in dying patients before and after removing the life support. Especially, they would analyze the temporal dynamics and functional connectivity patterns in their brain across all frequency bands. So moving on to methods. For this study, they identify 4 patients as participants. And these 4 patients were all admitted in intensive care before they died, and they later pass away due to cardiac arrest-induced anostic injury. The EEG monitoring. And they were under EEG monitoring the whole time they were in the intensive care, which gave rise to EEG recording of their brain signals from before they died, like the few hours they died, to after removal of life support. And the authors analyzed these data and analyzed the brain activity at all frequency bands. So as like a start, they first analyzed the absolute EEG power in each frequency bands in each of the 4 patients, because they expect there will be variability in the neural activity patterns in each individual participants. So what they found was that in participant 1 and 3, immediately after the removal of life support, there was a surge of gamma power in prefrontal and central areas, in frontal and central areas in the brain. And a few seconds after that, there was a surge of gamma power observed in the left anterior mid-temporal lobe. And that kind of surge persisted for a few more seconds. However, this surge of gamma power was not observed in participant 2 and 4. So in the following analysis, they decided to focus their analysis on participant 1 and 3's data. And in participant 1 and 3, they first analyzed the coupling between the phase of low frequency band neuroactivity with the amplitude of the high frequency band activity. And this is called the phase amplitude coupling of brain activity. And high level of coupling suggests a synchronization of brain activity across bands, signaling the kind of dynamic integration of neural activity in, let's say, local region. And what they found was that this kind of coupling was not evident before the removal of the life support, but right after the removal, there was an increased coupling in right anterior mid-temporal lobe, somatosensory cortex, and dorsolateral prefrontal cortex. So it's quite a global surge of coupling. And that also suggests there's some kind of local integrative activity within each of these regions. And the next question is obviously that what about the communication between regions? So first of all, continuing investigating the phase amplitude coupling, they found that the phase of low frequency band activity in prefrontal cortex is coupled with high frequency waves in the posterior regions, specifically the TPO. And that suggests some kind of communication between these 2 regions. And then, aside from the phase amplitude coupling, they were also interested in the functional connectivity within each brain region and across brain regions. So this functional connectivity basically tells you how brain activity in each frequency band correlates between brain regions. For example, whether gamma activity in one region correlates with the gamma activity in the other. And if they correlate, it means there's some kind of high frequency signal communication between these two regions. And using this method, what they found was that there's an increased functional connectivity across low and high frequency bands within the TPO junction, so the posterior hot zone that they identified in their prediction. And also increased gamma band connectivity between TPO and prefrontal cortex, both right after removal of life support. This functional connectivity analysis basically revealed that there's some kind of communication within the TPO junction and from between TPO junctions and prefrontal cortex right after removal of life support. And then they were also interested in the direction of this communication. So, who feeds forward to who and who feeds back to who. And so they use this analysis called directed connectivity analysis. And what they found was that there was an increased feed-forward activity from TPO to PFC and PFC feeding back to TPO. In summary, the authors found that in near-death stage, especially immediately after removing life support, patients' brains become, quite active. Specifically, there was a global surge in gamma band activity, and this gamma band signal communication within TPO, which is the posterior hot zone, and also from TPO to prefrontal cortex and from prefrontal cortex to TPO. That's it. It's a really tough paper to summarize because they have many local neural activity patterns that they found, and it's impossible to identify all of them in a summary. I'll otherwise be reading the entire paper. Okay, do you have any questions or anything to add?
Not, nothing to add, but a question, but we can just go straight to the discussion for this paper. Yes. Yeah. So yeah, the paper, they agree in the discussion that it's really, by the way, the data they obtain looks really interesting. But the point is that it's really difficult to interpret the data. So from here, what we can say is that, yeah, sure, we have brain activity after the removal of oxygen support. Yeah, for me, it's like, yeah, sure. And then they investigate various different types of neural activities. That's also interesting. But it's difficult to interpret. Okay, then this neural activity is linked to what kind of functions, for example. Of course, here, you mentioned, they mentioned in the discussion and introduction that maybe during the heart stop, people may have some conscious experience, maybe as brains still active, but we don't have any subjective report in this case, in this paper, so we can't say anything about that. But I think in the discussion they try to link some homeostatic function to these neuroactivity, and that can be interesting. The reason why is that in a sense, in participant subject were in a really extreme condition, so the body tried to keep the like a heart rate or breathing So that kind of, activity or the brain activity related to these, physiological, behavior or activities can be strongly related in the EEG data. So maybe that's, sounds interesting. But again, my impression is that, it's really difficult to interpret this data.
So what you were saying is the heightened activity in the brain right after removing oxygen support can relate to the body's attempt to survive.
Yeah, something like that. Yeah, I think they mentioned something in this discussion. Also, after the oxygen support, the physiological, behavior will have, several stages, I think. Like the first stage, like we have this activity behavior. And then after that, we have this. So I think maybe like, I think something like that mentioned in the discussion, like at some point, the heart rate start to decrease. And that will, I don't know what first, but like a first breathing, and then maybe heart rate decrease or something like that. And then maybe we can, relate these activity with neural activities.
So I see. So the brain activities could be related to these physiological changes, but not necessarily correspond to any conscious experience per se.
No.
And also in the introduction, they also mentioned that only 10 to 20% of survivors report this near-death experience. It would be unlikely for them to kind of randomly sample 4 people and then 2 people have already, 50% already have near-death experiences.
Yeah, another point is that, they had 4 participant subjects, and then they could find these neural activity only from 2 subjects. But I couldn't, did you find any, discussion part or method part mentioned why this is the case? I think they mentioned something about seizure, a history of seizure. Yes, but they said that, interestingly, so they didn't expect that, history of seizure related to this, neural activity after the oxygen support.
What they said is in participant 1 and 3, in which they found gamma power surge, happens to have history of seizure.
Yeah.
Although, they had seizure experts to look at their brain data 24 hours prior to life support removal and confirm that that's very unlikely for them to have seizure. However, they also suggest the possibility that this increased high-frequency band activity can be seizures happening in some deep brain areas, which is not clearly captured in EEG.
Yeah, I remember that part. But again, that's also really difficult to interpret. So the first, the point I made 2 points. The first is that, they observed many different neural activities, but it's really difficult to link these neural activity with some functions. And the second is that, they observed these neural activities only 2, subjects from 4. And I don't know why. Only 2, not all of them, not from all of them. That's the difficult part for me.
Well, I guess the explanation could be if gamma band corresponds to near-death experience, then it makes sense for it to not appear in some participants, but not the others.
Okay, so maybe, so basically you're saying that the two participants had that experience, but the other did not, or something like that.
But if gamma band activities correspond to NDE, but it's what I said before. If already 2 people out of 4 have NDE, then NDE should be more prominent among the cardiac arrest survivors than this. Well, the sample size is very small, but without actually knowing whether near-death experience happens, there are many explanations to this. And also, they didn't touch too much on the low frequency band activities, but in many of their analysis, there are persistent, low frequency band activities. I wonder what their functions are. And
Just I
understand that they're focused on gamma oscillations, but if slow wave activity correspond to actual decrease of awareness, just like deep sleep or something like that, then it will make sense. If they found, let's say if they found increased slow wave activities in participant 2 and 4, like the 2 participants that they did not do further analysis on, or did not do too much analysis on, then that would be an interesting comparison. Like, for example, in figure 1b, you know how S1, so stage 1, before they remove life support, there are some really strong theta and alpha band activities. Well, you can say they're just sleeping or something, but but they did not mention anything about them.
No. Again, my take from this paper, or what they tried to do was interesting. I mean, the data they obtained, interesting. But again, it's really difficult to interpret the data. That's the point. And I don't have anything to say more than that.
Any improvement, like if you were to do a follow-up study, what kind of things you would do to address
follow-up
that
study?
Man,
follow up.
Not like using the same data set per se, but if you were to investigate near-death experience and you want to know whether gamma oscillation is associated with near-death experience, right?
Wait, maybe. One potential research project I can imagine that, if we have a really great brain decoder, and we can reconstruct subjective experiences based on brain data, for example. And then, we can see what kind of experience they had. And then you mentioned that, these alpha gamma band activities kind of indicate the potential conscious experiences, right? So we can say that, for predictions that we should be able to decode some experiences from the participant with gamma oscillations, but we should not be able to do that for the participant without gamma. Something like that.
Yeah, I've seen some recent papers on reconstructing the image you see based on the brain activity when you see the image, right?
But
I don't know the mechanism of how they work, whether they're they train the classifier in a particular way in order to decode.
Yeah. But I know that the brain decoding itself is really challenging, and it's almost impossible if we use EEG. I mean, if we want to have a picture of the experiences, it's gonna be really difficult.
I see.
Yeah, but there's some research going on, like decoding, reconstructing experiences using MRI, fMRI data. And then we can see what these people experiencing.
Yes.
Yeah, that's a kind of potential research project I can imagine. But again, there are many technical difficulties, and also it's I don't know how they obtain this data. I mean, of course they could obtain data because I think one of them or a few of them are medical doctors. So, but it's really difficult to access these kind of data. So there are many difficulties.
When it comes to access, do you mean like
ethical? I didn't check the ethics part of this paper carefully.
You said it was approved by internal review board at the University of Michigan.
Yeah. It's approved, but
Oh, and this is a retrospective study. It's not like, oh, we have 4 patients in intensive care. Then we go ask their families whether they want to get EEG data recorded after they die. It's like tell them, oh, they're probably gonna die. So can we get the neuro? It's not like that. It's a retrospective study. And these patients were in the neuro intensive care unit. So I think what that means is that if they're admitted to this unit, then they are pretty much likely to have EEG monitoring as part of the intensive care.
I see. So this EEG recording is a kind of part of their, treatment or some, clinical purpose.
Yeah.
I see.
Alongside with the ECG, which is the thing that monitor heartbeat.
Yeah, that makes sense. And that made me okay, then if that's the case, then it's gonna be really difficult to do the research I propose.
Why is that?
Because I was kind of imagining using MRI, not EEG.
Oh, I guess with all the other life support putting on the participants, it's probably hard to let them go through MRI scans, I guess, fMRI scans. Some of them are on ECMO even. So yeah, EEG is probably the most viable option.
Yeah, but if we use EEG, it's a my impression is it's almost impossible to,
do any decoding.
Yeah.
I mean, decoding images may be really hard, but are there any studies that decode like auditory signals?
Yes, I think, yeah, several study try to decode, sounds.
Oh, right, internals, like the ones that decode like your internal speech. I think I've heard of that.
Yeah, that's, yeah, maybe. But, one of my friend, he did, decoding of sounds, reconstruction of sounds based on MRI data. So basically, you present them, some audio stimuli like music or just, artificial stimuli to participant. Then brain record the MRI, fMRI, then try to, again, reconstruct. So try to generate the stimuli the participant had based on the MRI activities.
The sampling rate of
Yeah.
is low, no?
Yeah. So yeah, I asked the same question to that friend. It's really difficult, right? Given the
Of course, like you sample like 15 seconds, every 15 seconds. Well, how are you supposed to decode anything coherent?
Yeah. So yeah.
So yeah, is it possible to decode from EEG data, like simple sound stimulus from EEG, or is it impossible?
I think some people try to do that, but again, if you use EEG, we don't have a good, spatial resolution.
I see.
So not easy. So yeah, it's
I was thinking about presenting stimulus to them, to the the patients, and then see if you can decode it. But you encounter the oldest problem ever, which is whether this is conscious experienced or it's just unconscious. Then fair enough.
Yeah. So, but again, in the summary you mentioned that in a near death situation, some people experience a series of life events in a short time window, right? And then if you can decode that, then that's gonna be, because at least me, I've never in that situation, so I don't know how it will be like. But if we can decode, reconstruct these experiences from someone, and then if these people survive, luckily after that, they can check whether what they experienced is consistent from what the researcher reconstructed from their brain activity, and then we can say, okay, that's
I'm not sure if this is ethical to do. Like, I'm not sure view that.
There again, I admit that there are many issues, not only technical but also ethical, and maybe there are some other issues, but that's something I guess interesting, or worth doing if possible, or the point is that from this paper, it's really difficult to link neuroactivity with some functions or experiences. So
I thought of you know, getting, let's say, data from more people admitted into intensive care unit,
Mm.
and then, you know, you bet at the chances of how many survive.
Mm.
At the same time, you also bet at, on top of that, the chance of this person, the survivor, have near-death experience. If you have data from many people, then you know, one or two may survive, and then one of them may have near-death experience, and then you can use that person. You can use that person's data and then compare that with their report or something like that. But then I realized maybe neuro-intensive care unit are people who have been suffering. How do I say this? You know, they have been suffering from some kind of disease for a very long time. And then when they're admitted into this intensive care unit, it's already, you know, the chance of survival is already very low. But compared to those who survived cardiac arrest, they and was able to report near-death experience, they probably get into the near-death situation from accidents. And when it's like these kind of life-threatening accidents, it's not neuro-intensive care unit they're admitted into, it's like a general intensive care unit they're admitted into, which does not come with EEG monitoring. So it's hard to get EEG data from, you know, intensive care patients who can survive to talk about whether they had near-death experience or not.
Yes, you know, yeah. Yeah, I don't have anything to add further. So, do you?
I don't.
Okay, then shall we wrap up discussion and then see you next week maybe. Bye.
Bye.